projectile is any object that moves through the air or space acted on by only gravity and possibly air resistance. Projectiles near the surface of Earth follow a curved path that at first seems complicated. These paths are surprisingly simple when we look at the horizontal and vertical components of motion separately. Projectile motion can be separated into components. Roll a ball along a horizontal surface and its velocity is constant because gravity doesn't affect its horizontal motion. Drop it and it accelerates downward and covers a greater vertical distance each second. What makes projectile motion simpler than it seems is that the horizontal component of motion for a projectile is completely independent of the vertical component of motion. Their combined effects produce the variety of curved paths that projectiles follow. This is a strobe light photo of two balls released simultaneously. One ball drops freely, while the other one is projected horizontally. There are two important things to notice in this photo. The yellow ball's horizontal component of motion remains constant. Gravity acts only downward, so the only acceleration of the ball is downward. Both balls fall the same vertical distance in the same time. The vertical distance fallen has nothing to do with the horizontal component of motion. The ball moves the same horizontal distance in the equal time intervals because gravity doesn't affect its horizontal motion. The path traced by a projectile accelerating in the vertical direction while moving at a constant horizontal velocity is a parabola. No matter what angle a projectile is launched, the vertical distance of fall beneath the idealized straight line path is the same for equal times. The dashed straight lines show the ideal trajectories of the stones if there were no gravity. Notice that the vertical distance that the stone falls beneath the idealized straight line path is the same for equal times. This vertical distance is independent of what's happening horizontally. With no gravity, the projectile would follow the straight line path. But because of gravity, it falls beneath this line the same vertical distance it would fall if it were released from rest. For the component vectors of the cannonball's motion, the horizontal component is always the same and only the vertical component changes. At the top of the path, the vertical component shrinks to 0, so the velocity there is exactly the same as the horizontal component of velocity at all other points. Everywhere else, the magnitude of velocity is greater because the vertical component of velocity is not 0. The velocity of a projectile is shown at various points along its path. Notice that the vertical component changes while the horizontal component does not. The angle you launch a projectile at affects how high and how far it goes. In this case, at 30 degrees, we have kind of a low angle. So it's not going to go very high because the vertical initial velocity vector is kind of small, but the forward velocity vector is kind of big. So what we're going to see is a fast to the right, but kind of low trajectory. So let's watch that. Ready? Right? Didn't go very high, but it went pretty far. Let's try it again. Now we're going to do it at a higher angle. We're going to do it way up at 60 degrees. Now, our vertical velocity vector here is rather large. The forward one isn't so big, so it's going to go really high, but not forward very fast. And let's see what happens. There you go. High, but short. All right, cool. Projectiles that are launched at the same speed but at different angles reach different heights above the ground. They also travel different horizontal distances. That is, they have different horizontal ranges. The same range is obtained for two different projection angles, angles that add up to 90. An object thrown into the air at an angle of 60 degrees will have the same range as at 30 degrees at the same speed. Maximum range is usually attained at an angle of 45 degrees. Without air resistance, a projectile will reach maximum height in the same time it takes to fall from that height to the ground. The deceleration due to gravity going up is the same as the acceleration due to gravity coming down. The projectile hits the ground with the same speed it had when it was projected upward from the ground. Without air resistance, the speed lost while the cannonball is going up equals the speed gained when it's coming down. In the presence of air resistance, the path of a high-speed projectile falls below the idealized parabola and follows the solid curve.